All right, sum and difference formulas. How can I use these formulas to solve problems? And there'll be multiple problem types. The nice thing is that other than the formulas, everything you see here is review. So each problem type is going to have some old skill from last semester or earlier in the semester, depending on what school year it is. All right, so here we go. These are the sum and difference formulas. Okay, we're not going to prove them. We're just going to be able to use these formulas. The proofs are pretty cool, but they're pretty tedious. We'll take these identities or formulas for granted. So sine of the sum of two angles is sine of the first angle times cosine of the second angle plus cosine of the first angle times sine of the second angle, and so on down the line. So you have a sine of a sum of two angles, sine of the difference of two angles. Cosine, sum and difference. And then you have the tangent sum formula and the tangent difference formula. So basically, in general, we're starting with the left side, some expression, and we're using the right side to find the answer. But we're going to also go in the other direction as well. So that's our goal today, to use the addition, subtraction of angles formulas for sine, cosine, and tangent. And then really the sum of two angles leads to what's called the double angle formulas, which will be our next lesson, which is just an actual shortcut when alpha and beta are the same. Of course, alpha plus alpha is 2 alpha. So if we were trying to find sine of 2 alpha, we would use the same formula, but we wouldn't need beta. So there's actually a quicker way if the two angles that we're adding are the same. Let's dive into the first example. In general, this is the most typical type of sum of angle formula problem or difference of angle formula problem. Cosine of 75 degrees, of course, I can type that in the calculator and get a decimal approximation, but the goal is if for some reason this angle can be written as a sum or a difference of two angles that I know for cosine, then I can actually use those formulas. For example, if I can rewrite 75 as a sum or a difference of angles that are in terms of 30, 45, and to be redundant because 60 is a multiple. If I can somehow rewrite 75 as some multiple of 30 plus or minus some multiple of 45, then I can use the formula. Here's what I mean by that. I know that 75 degrees is 45 degrees plus 30 degrees. Okay? Therefore, let's look at the formulas. There is a formula that says if I'm adding two angles, if I'm finding cosine of the sum of two angles, then it's going to be cosine of the first times cosine of the second angle minus sine of the first times sine of the second angle. So I'm just going to straight apply the formula. Skirt, skirt. All right, so that means that we have cosine of 45 times cosine of 30. Skirt. And this is the weird thing, right? For the cosine sum, it's actually a difference. So to memorize, cosine is cosine, cosine, sine, sine, but adding is subtraction. Subtraction is adding. Little patterns you're going to look for. So I'm using this formula once again. So for a sum of two angles for cosine, it's actually a difference when you apply the formula. And now I can actually evaluate this. I know what cosine of 45 degrees on the unit circle is. That is root 2 over 2. I know what cosine of 30 degrees. Cosine of 30 degrees is root 3 over 2. Sine of 45 degrees is also root 2 over 2. And then sine of 30 degrees is 1/2. This is the most typical sum of angle, difference of angle formula problem for the trig functions. So you rewrite in terms of something you know on the unit circle, and then of course you make your substitutions So this gives me root 2 times root 3, and at this point it's all being careful. That's root 6 over 4. 2 times 2 is 4. Minus root 2 times 1 is root 2 over 4. And therefore you can rewrite this as root 6 minus root 2 all over 4. Nothing you can do to simplify that. End of problem. All right, so that is, let's put it all on one slide. That is the most typical type of problem, cosine of an angle in terms of degrees. What about if it's in terms of radians? Same concept, a little bit trickier. Okay, so now radians are a little bit more difficult to see. It's easy to see that 75 is 30 plus 45 in degrees. Not so easy to see pi over 12, but check this out. So I do know that pi over 12 is 3 pi over 12 minus 2 pi over 12. Okay, now why does that matter? Well, because I know that 3 pi over 12 is pi over 4. And I also know that 2 pi over 12 is pi over 6. So once again, if I can take an angle that's in radian, it's in radians form, and if I can rewrite it in terms of a multiple of pi over 4, pi over 6, or maybe even pi over 3, some multiple, then I can rewrite this using those formulas. So cosine of pi over 12 is, so pi over 12 is pi over 4 minus pi over 6. So this takes a little bit of fumbling around, and there are only so many combinations of numbers you'll see. Generally, you'll see pi over 12, pi over 2, something over 2, something over 12. So you're just playing with all the different ways you can rewrite the given radian value in terms of those three. Okay, and some multiple. It might be 3 pi over 4. It might be 7 pi over 4. Okay, so they get, tricky, but it takes a little fumbling around. So that first initial step is kind of the tricky part. After that, straight go through the procedure. So cosine of a difference of two angles. So let's come over here, look at the formulas. Cosine of a difference, so we're using this formula. So cosine of a difference is similar to the last problem because we have a difference. We're going to have a sum, cosine, cosine, sine, sine. So I'm looking for the pattern. So let's go back over to the problem. So that means we have cosine of pi over 4 times cosine of pi over 6 plus sine of pi over 4 times sine of pi over 6. Now it's straight unit circle. Now at this point we've done the unit circle so much you don't have to make a little sketch off to the side, but if you want to, cosine of pi over 4 is root 2 over 2. Cosine of pi over 6 is root 3 over 2. You guys know I like to make silly mistakes all the time. Shameless. Not an engineer. I'm a goofy mathematician. Or a math teacher, let's be real. Alright, sine of pi over 4 is root 2 over 2 times sine of pi over 6 is 1/2. Okay, so the trickiest part once again is splitting that angle into a sum or a difference of two angles of which you know the value of which you know the value of. See, I'm an English major too. And then you make your substitutions. Now you just have to be careful with the arithmetic. Root 2 times root 3 is root 6 over 4 plus root 2 over 4. And you notice for most of these problems, you're going to have something in terms of root pi over 4, something in terms of pi over 6 or pi over 3. So you're seeing the same numbers over and over. We haven't seen a problem yet where we had a 0 involved or a 1 involved. But numerically, you see a lot of root 6 over 4s, a lot of root 2 over 4. So this becomes root 6 plus root 2 over 4. Final answer. Okay, so there is example 2. So example 2 is, here's all the work, and you don't have to show what I'm circling using the highlight. You don't have to show that, but that's, to me, that's where you're going to spend some time fumbling around with those numbers. And then after that is just straight substitution. All right, example 3. So examples 1, 2, and 3 are just, here's a problem, rewrite the angle as a sum or a difference and apply the formula. Then they get a little bit more complicated and we go back to some of the old concepts. So tangent of 15 degrees, when I see 15 degrees, I need to rewrite 15 degrees in terms of 30, 45, 60, or some multiple. So when I see 15 degrees, I'm thinking 60 minus 45. It's one possibility. Okay, it could be 45 minus 30. Two different problems that will end with the same result. So I just want you guys to know, before you even start this problem, when you split the angle into a sum or a difference, generally, I mean, there are going to be lots of different answers. Sometimes there's a most obvious one. In this case, not at all. So I'm going to use tangent of, all right, so we have tangent of 60 degrees minus 45 degrees. 60 minus 45 is 15, so we're good so far. Now we go to our handy dandy set of formulas. Tangent of a difference, which is what we're looking at. So difference in the numerator, sum in the denominator. So nice pattern. Difference. If it were a sum of two angles, I would have a sum and a difference. So each one of these formulas are virtually the same, except for the adding and subtracting on the right-hand side. Okay, so if you look at, there's a nice pattern. So we are using this formula. Okay, so I'm got it. So that means, to apply the formula, we have tangent of 60 degrees minus, same operation, tangent of 45, both of which I know, over 1 plus, look at me, tangent of 60 degrees times tangent of 45 degrees. Now you're going to see some old stuff you haven't seen in a while. When you have a radical expression over a radical expression, you're going to have to multiply by the conjugate, all kinds of good stuff. So this one's a tough one. So make sure that you know, when you work these problems, just make sure you're comfortable with the process. You might have to work the same problem a couple times until you're comfortable. All right, tangent of 60 degrees, root 3, minus tangent of 45 degrees, that is minus 1 over 1 plus root 3 times 1. So then I simplify. Root 3 minus 1 over 1 plus root 3. So I just want to remind you guys, when you have a radical expression over a radical expression, if it is a binomial, so if you have a binomial in the denominator, a way to get rid of that is to conjugate. And here's what I mean by that. Since I have 1 plus root 3 in the denominator, I'm going to multiply the top and bottom by 1 minus root 3. So just to be clear, 1 plus root 3, 1 minus root 3, those are called conjugates. When you multiply them out, when you FOIL them out, the radicals disappear, and you have rationalized the denominator. You've gotten rid of the radical. All right, so let's see what happens. The numerator still might have a radical, but the denominator will not every single time. So I'm going to FOIL. Root 3 times 1 is root 3. Root 3 times root 3 is 3, so I have minus 3. Negative 1 times 1 is negative 1. Negative 1 times negative root 3, positive root 3, all over. Now, there's a shortcut to conjugates if you FOIL it out. So 1 times 1 is 1. The outside and the inside product will always cancel out. That's the beauty of conjugates, and you're left with root 3 times negative root 3, which is negative 3. So every time you multiply a radical expression times its conjugate, the radicals cancel out, which is the goal. So now I have negative 3 minus 1. So I have negative 4 plus 2 root 3. So 1 root 3 plus 1 root 3 is 2 root 3, all over negative 2. Now, there are a lot of times where these three terms are not all divisible by the same value, and so you might be done. So if this were 5 root 3, you would just circle that fraction. You'd be done. But in this case, both components of this fraction can be simplified. So I have negative 4 divided by negative 2, which is 2. 2 root 3 divided by negative 2 is negative root 3. Final answer. So let's make sure we can see this whole deal. Example 3. Boom, there it is. Okay, so once again, find the difference or sum, make the substitution, use the unit circle, and then rationalize that denominator. All right, that's example 3. Now we can also use these formulas in the other direction. I have no idea what sine of 80 degrees is. I could do that in the calculator. I could find a decimal approximation. That's no good. Same thing with a trig function at 20 degrees. Okay, but I'm looking at 80 and 20, and I'm thinking I know what 80 minus 20 is. 80 minus 20 is 60. So if I can rewrite this as sine of or cosine of 80 minus 20, that would be fantastic. So let's look at the formulas and see which formulas have sine, cosine, minus cosine, sine. And here it is. Bow. Sine, cosine, minus cosine, sine is going to be sine of the first angle minus the second angle. So this, according to the formula that I just circled, is sine of 80 minus 20, which is sine of 60 degrees, which is sine of 60 degrees, root 3 over 2. Final answer. Now, I want you to do this. I want you to make sure that your calculator is in degrees, and I want you to type in sine of 80 degrees times cosine of 20 degrees minus cosine of 80 degrees times sine of 20 degrees, and get 0.866 something. And then I want you to type in root 3 divided by 2. You'll get the same answer. So the beauty is, for every one of these problems, you're using the formula, right? You're being faithful to the formula and hoping it works. And then at the end, you can go back and just check your work. So let's run back to example 1. You could type cosine of 75 degrees in your calculator. You'll get a decimal approximation. Then you could type root 6 minus root 2, enter, divided by 4, and then show that those two decimal approximations are the same. So you can feel good about your answer. You can do a quick, just numerical approximation check. Example 2, you can type cosine of pi over 12 in your calculator. Make sure that it's in radians. And then you can type in root 6 plus root 2, all divided by 4. And you can actually show that those are the same. Same thing with tangent. So you can type tangent of 15 degrees in your calculator, get some crazy decimal, and then 2 minus root 3, enter. And you'll see on your home screen on your calculator that tangent of 15 degrees gives you a decimal. 2 minus root 3 gives you the same decimal approximation. So I just wanted you guys to know that as you're doing these numerical problems that are a lot more basic than what I'm about to start doing, you can do a quick check. Okay. All right. So now the problems are going to be a little bit more involved. You're going to actually apply some of the stuff from previous sections. So cosine of pi over 2 minus theta, I want to verify. I want to actually show or prove that this value must be the same as sine theta. So I see cosine of a difference of angles. So I'm going to go to my formulas. Cosine of a difference. So I'm going to apply this formula. So alpha and beta are pi over 2 and theta. Okay, just to remind you that when you see cosine of a difference, that's going to be cosine, cosine plus sine, sine. So remember, the proof begins with rewriting the more complicated side. Okay, which is the same as cosine of pi over 2 times cosine of theta minus, oh, I lied, plus sine of pi over 2 times sine of theta. How do I know that? That is one of my difference identities. So I'm just going to write some difference. Now you can write ID or formula. I'll put ID. If you put formula, that's fine. In general, these are called the formulas, but they are identities, and an identity is a formula as far as trig is concerned. Okay, there are formulas that aren't really identities as much as just useful in science. Okay, but for this course, for a highly abstract mathematics, identities and formulas, same. All right, so now let's just simplify. Let's see what happens. I know what cosine of pi over 2 is. Cosine of pi over 2 is 0. So I have 0 times cosine of theta plus, I know sine of pi over 2 is 1 times sine of theta. How do I know that? That's just unit circle. All right, so we just know those values from the unit circle. And then we simplify. 0 times cosine of theta is 0, plus 1 times sine of theta is just sine of theta. How do I know? I just simplified. All right, end of proof. So we've done identities before. Now we are just throwing into the mix these sum or difference identities. And you can be more specific. This actually is a, to be specific, this one is a difference. This is one of the difference IDs. Apologize for that. That was my dog. He wants me to play. Can't play right now, buddy. That's bingo. He's still a puppy. All right, so that takes us to example 6. Now we're really getting into a lot of the stuff we've done in the past, and I'm going to make a sketch. You do not have to make the sketch I'm going to make, but I'm going to make a sketch for each of these. So now I'm going to find 3 different values. So 6 part A is find sine of alpha plus beta, part B, part C. So part A, I know that sine of alpha is given. So sine of alpha is 4 over 5. And knowing that alpha is between pi over 2 and pi is important. That means that alpha is in the second quadrant. We'll come back to that. And then we're also given sine of beta, where beta is between pi, 180, and 3 pi over 2, which is 270. So this is saying that beta is in the third quadrant, and this is saying that alpha is in the second quadrant. Okay, so let's look at this. Let's see what will happen. So I'm going to make 2 diagrams. You do not have to make the diagrams, but the diagrams should help. So I know, and this is going to be a quick recap of some of the skills from last semester or previous sections. Pi over 2 pi. So alpha is in the second quadrant. I know that sine by definition is y value over r. So for alpha, when alpha is involved, I do not know x, but I know that y is 4 and r is 5. So I'm going to make a quick sketch. So 1, 2, 3, 4. So my y value is 4. Now, here is alpha. I don't know if you guys remember. That was a little weird last semester when you had to draw an angle from the first quadrant, from the x-axis, into the second quadrant. So that's alpha. So right now I know that y is 4. I do not know x, but I do know So I'm going to call this is the x value I'm trying to find. All I know, I don't know what x is yet, but I know that x is negative. So I'm going to use the quadratic formula, x squared plus 4 squared equals 5 squared. And just a reminder, and we've seen this a lot, anytime you have a 4, 5, 5 is the hypotenuse. This is a 3, 4, 5. So if you solve for x, 25 minus 16 is 9. X is either going to be positive or negative 3. Since we're in the second quadrant, x has to be negative 3. So that's going to come into play in just a minute. Okay? So that's our first, that's alpha. Now we need to also draw a diagram for beta. There's bingo again. Apologize, students. All right, so now I know that for beta, we're given a sine value. So sine of beta, my y value is negative 2. Okay. My r value is root 5. Once again, I do not know x. So if I were given cosine, I'd be given x and r, but I'm given sine. Hopefully you kind of vaguely remember this from last semester. So I know that the hypotenuse is root 5 long. I know that the height of the triangle is 2, even though y is negative 2, the height is 2. Once again, I do not know x, but my angle is there. That is angle beta. So beta starts in the first quadrant on the x-axis, and there it goes. So Pythagorean theorem again. So I have x squared plus negative 2 squared equals root 5 squared. So x squared plus 4 equals root 5 squared is 5. Just a reminder, anytime you have a number squared, it is positive no matter what. So x squared equals 1. So x is either going to be plus 1 or minus 1. Now, since we know x is to the left in the third quadrant, x has to be negative 1. Okay, so we now, for angle alpha, so for this example, we have, all right, so now we've done all the hard work. Now we can do parts A, B, and C quickly using those formulas. Okay, so let's go into part A now that we have all the pieces. Now, sine of alpha plus beta, let's look at the formula. Sine of alpha plus beta is sine cosine, cosine sine with a sum. So this is sine of alpha cosine of beta plus sine of beta times cosine of alpha. Now let's go back over there and look at it. You can see how I switched these two terms. All good. All right, so let's make our substitutions. Now, according to all that work we did a minute ago, sine of alpha. Now, sine of alpha is given, so sine of alpha is 4 over 5. Cosine of beta, so let's go back to our work. For beta, cosine is going to be negative 1 over root 5. So cosine of beta is negative 1 over root 5 plus sine of beta. Let's go back to our work. So for beta, sine is going to be negative 2 over root 5, which was given. Sine of beta is negative 2 over root 5. So that's negative 2 over root 5 times cosine of alpha. Let's go back to our work. So cosine of alpha, so alpha's here. So cosine is going to be negative 3 over 5 times negative 3 over 5. So for every one of these problems, you're going to use the formula, and then you're going to have to use the diagram for alpha to find x, y, r, a diagram for beta, x, y, r. So that takes us to 4 times negative 1 is negative 4. So I have negative 4, 5 root 5. I don't want to rationalize anything yet until the very end. You'll see that pattern over and over. Negative 2 times negative 3, positive 6, over 5 root 5. Okay. So negative 4 plus 6 is 2, over 5 root 5. Now, especially if you were in delta math, you got to be careful. So now you want to rationalize. So now I'm going to rationalize. I'm going to multiply top and bottom by root 5. Okay, to rationalize. So I get final answer 2 root 5 over, now root 5 times root 5 is 5 times the other 5 is 25. Final answer. All right, so that is part A, and then parts B and C are going to be very similar. At this point, if you want to take a minute, try B on your own, try C on your own, and then skip to my answer, you can do that, save yourself some time, or you can just watch me work this problem as well. So exact same process as part A. So cosine of alpha plus beta is going to be this formula. So that takes us to cosine of alpha times cosine of beta minus, so we have the minus. So for cosine, the sum and difference formulas, the sign changes. So for a sum, it becomes subtraction, sine of alpha, sine of beta. Same values from before. So our cosine of alpha was 3 over 5, but it was negative. Go back to all that original work. Cosine of beta, right? So that was negative 1 over root 5. We go back just to make sure. Negative 1 over root 5, yes. And then you have minus sine of alpha is given. That's 4 over 5. Times sine of beta is given, negative 2 over root 5. So now we simplify just like before. 3 over 5 root 5 plus, be careful with the arithmetic, 8 over 5 root 5. 3 plus 8 gives us 11 over 5 root 5. Rationalize like before. 11 root 5 over 25 once again. Final answer. Okay, and then that takes us to part C. All right, part C, we're going to use tangent of alpha minus beta, which is that formula. So tangent of alpha minus beta is tangent of alpha minus tangent of beta over 1 plus tangent of alpha times tangent of beta, and now is where we have all kinds of fun, right? So tangent of alpha, go back to our original work. Remember tangent by definition is the y-coordinate over the x-coordinate. So if I go back to all that original work, we have to look at alpha. So we're going to have 4 over negative 3 for tangent alpha. And then for beta, it's going to be negative 2 over negative 1, which is going to be positive 2. Okay, so let's go back to, and let me just write that up. So for alpha, we had our y and our x value for alpha, and then for beta, we had our y and our x value. So 4 and negative 3. Just a reference. So tangent of alpha, 4 over negative 3, or negative 4/3, plus tangent of beta is negative 2 over negative 1, which is positive 2. Then we have 1 plus negative 4 over 3 times 2. Now, this is something we did not see in our first tangent example, but we'll see in this one. Just for the sake of actually saving time, you don't have to do this, but you'll see this pattern a lot. I'm going to go ahead and multiply just because that's going to work out nicely. So 4 over 3 times 2 is 8 over 3 minus sign. Now, I have fractions in the numerator and the denominator in terms of 3. I'm going to multiply the numerator and the denominator by 3. Now, you don't have to do this. Some of you are like, I'm not going to do that. But I like to, anytime I have the same denominator within fractions in a fraction, I just go ahead and eliminate them. So watch what I'm doing here. Once again, you do not have to do this. You can use other methods to simplify, but I think it's kind of cool to see this because it's nice when there are variables involved. So negative 4/3 times 3 is just negative 4. 2 times 3 is 6. Okay, fractions are gone. 3 times 1 is 3. Negative 8/3 times 3 is just negative 8. I personally like to do that anytime I have fractions within fractions and all the fractions involve the same denominator. So now I can just simplify a lot quicker. Answer is negative 2/5. Okay, so if you just wanted to do negative 4/3 plus 2, right, and get 2/3, and then in the denominator subtract and get what, negative 5/3, and then keep change flip and all that, that's fine. But I just wanted to show you that when there are variables involved or radicals involved, this little trick here will save you some time. All right, so that is the end of example 6. So that's a recap. So really we did one problem similar to what we did last semester, a second problem similar to what we did last semester. We found x, y, and r in terms of alpha. We found x, y, and r in terms of beta, and then we were able to apply the formula and make a lot of substitutions. So you'll see problems like that in the homework. Tedious, but not bad. All right, so now very similar. I think this problem, for me, this is just my opinion, this problem I think is a lot less work, a lot less tedious than example 6, but very similar. So here we go. So before I do parts A, B, and C, I'm going to make a sketch. Since we're given sine of theta is 2 over 3, and theta is in the second quadrant, this is, once again, I have no idea where 2/3 is on the unit circle. It lives on there, but I don't know what angle gives me 2/3 for sine or cosine or tangent. So this is one of those problems that involves x, y, and r. So I'm going to make a sketch. I know theta is in the second quadrant. We're given sine, so we're given the y coordinate is 2, the r coordinate is 3. We do not know x yet, but I do know that the y coordinate is 2. There's r, which is 3, and my theta is there. So theta is an angle that is between 90 degrees and 180. Okay, so now we can use the Pythagorean theorem. X squared is 5, so x is positive or negative root 5. Since I'm in the second quadrant, that means that the x coordinate must be negative root 5. Okay, so now I have, here's the nice thing, I don't have to do that twice in this problem. All that matters is theta. The other angles will be actual pi over 3 in this case, pi over 4. Those are values I already know on the unit circle. So now I can dive straight into these problems knowing that the x value, the y value, and the r value are given. So the first problem is simply find cosine of theta. Well, cosine of theta is x over r, and the x coordinate in this problem is negative root 5, and the r value is 3. Done. Nothing to do with this, the sum or difference formulas. Okay, that takes us to part B. So part B, if you want to pause and try this on your own, at this point you've seen everything that would help you be able to do a problem like this. We have sine of a difference. So sine of a difference is the second formula in our list. Sine cosine minus cosine sine. So let's go. Sine cosine. Now, because it's a difference, it's still a difference for sine. So the sine, the sines for the sine function stay the same. The sines for the cosine function switch. So now we have minus cosine theta times sine pi over 3. And guys, when I'm doing this, my eyes are going cross. So let me just make sure. Yes. Okay. So let's zoom in a little bit. Getting old. No, not really. Okay, so sine of theta. Now we already know sine of theta. Sine of theta was given, so I make a substitution. So sine of theta is 2/3 times cosine of pi over 3. Cosine at pi over 3 is 1/2 on the unit circle. Cosine of theta is negative root 5. This is where you have to be careful with your signs. Over 3 times sine at pi over 3 is root 3 over 2. So we simplify, and here's the beauty. You notice all these denominators are always the same. So I have 2 over 6. I am not going to simplify because in a minute we're going to see we're going to combine. So I'm subtracting a negative. So I'm adding. Root 5 times root 3 is root 15, which is simplified already. Nothing to do with that. Over 6. And now I can rewrite it as 2 plus root 15 over 6. Now here's what I was talking about in one of our previous examples. I have a 2 and I have a 6. I can reduce that, but there is no coefficient that has a factor of 2. So I am done with this. Now if you want to split this, 2 over 6 is 1/3 plus root 15 over 6, which cannot be simplified. You'll be tempted to do something with that. That's fine. But anytime you have a sum of two fractions, one fraction is considered simplified. I'll accept either one of those. Delta Math probably won't. All right. When and if you have this on Delta Math, I would run with the first one. That's considered simplified. All right, guys, we are almost done. Takes us to C, which will have a lot of weirdness with simplifying. All right, so tangent of a difference. That takes us to the formulas. The difference formulas here. So we have tangent of theta minus tangent of pi over 4 all over 1 plus tangent of theta times tangent of pi over 4. Now, let's go back to that original and look for x and y. So what were x and y? So 2 over negative root 5. So y is going to be 2. X is negative root 5. So that's going to be. So tangent of theta, 2 over negative root 5. Now I'm going to leave that as it is temporarily. Minus tangent of pi over 4 is 1 over 1 plus 2 over negative root 5 again times 1. So let's simplify. So that's going to be 2 over negative root 5 minus 1 all over 1 minus 2 over root 5. Now, and I forgot my root 5. Y'all keep me straight. If we were in class, you'd say, don't forget your root 5, Spires. You're right. Okay. Now, once again, I'm going to use that trick. And this is where I was talking about earlier. If you have a radical involved, or if you have a variable involved, you would want to do what I'm doing now. Multiply the numerator and the denominator by root 5. That's going to clean this up way quicker than any other method. So 2 over negative root 5 times root 5 is just negative 2. Negative 1 times root 5 is just that, negative root 5. Over root 5 times 1 is root 5. Minus 2 over root 5 times root 5 is just 2. So now, once again, you're going to multiply. So now we have a fraction that has one, it's just one fraction. We don't have fractions within fractions. So we still, because we have radicals in the denominator, we still have to multiply by the conjugate. Now I'm going to tweak, I'm going to write this not quite, I'm not using the convention, but that's okay. So for the conjugate, the key is that you want the signs to alternate. All right, so instead of root 5 minus 2, I'm going to write root 5 plus 2. That will get the job done. Now, just to be clear, we took this value and we multiply by root 5 over root 5. We multiply by 1. So when you multiply a number by 1, it looks different, but you didn't change the actual value of it. I'm now taking a number and I'm multiplying by a number divided by itself, which is also 1. So I'm now taking this problem, this expression, and I'm multiplying it by 1. I'm not changing the value of it, I'm just changing the way it looks. And I'm doing that because here I can't have a radical in the denominator and I can't have a fraction within a fraction. Now, this expression is not considered simplified, going back to Algebra 2, which you blasted through last school year. You can't have a radical in the denominator, and this is a way to deal with that. So now we need to distribute, and then everything should work out. So negative 2 times root 5, negative 2 root 5. Negative 2 times 2 is negative 4. Okay, so now negative root 5 times root 5 is negative 5. And then negative root 5 times 2 is negative 2 root 5 again. Now, we'll still have numerator, we'll still have radicals in the numerator, that's fine. Generally that's the case, but in the denominator there will not be. So root 5 times root 5 is 5. The outside and the inside products will always cancel out. That's the purpose of multiplying by conjugates. And then negative 2 times 2 is negative 4. So this one turns out really nice. So I'm going to work up. So let's kind of swing up here. So negative 4 minus 5, negative 9. Negative 2 root 5 minus 2 root 5 is negative 4 root 5 all over 1. Now, if this were any number other than 1, I would just put it on and make a fraction out of this, but I don't need to write over 1. Final answer. So, to kind of bring it all home, the tangent problems almost always involve a fraction inside a fraction, which you can eliminate, right? The denominators of those two fractions will always be the same, so you can multiply top and bottom by that denominator. You can always do that. And then if you still have a radical in the denominator, you will multiply the numerator and the denominator by the conjugate of the denominator. So just alternate the signs, the purpose of which is to eliminate the radicals or the square roots in the denominator. All right, guys. Well, that is any and every problem type that involves a sum or difference identity or sum or difference formula. So, just under 50 minutes. Definitely watch the video. Definitely work these problems. They're not difficult problems, but they're tedious and it just takes practice. So good luck. Look forward to seeing you guys in the actual classroom. We'll have more time this semester, so we'll actually be able to do a little bit more chatting and a little bit more direct instruction and a lot more Q&A. So, see you guys in class. Be safe, guys.